Right, okay, so I guess thanks for coming. The title of this talk is Revisiting PAC Learning, and it's based on just 3 different papers. It's kind of presenting like a line of work that I've been doing together with students and collaborators over the past few years. And I think most of it will be highlighted just to explain what are the results and make a few glimpses of some techniques also for the last 2 of the results. Okay, so what's the setup? I really want to thank my student first for preparing this first half of the slide. So we're looking at binary classification in the so-called realizable case. So what's the idea here? So we have a machine learning task. For instance, we get pictures of animals and we have to say or predict whether this is a picture of a mammal or not. Right? So the 2 classes are yes and no in this instance. And for this task, we have to come up with a learning algorithm. And the learning algorithm receives as input these labeled samples, right? So in this case, images with the correct label annotated onto the image, whether it's a mammal or not. And the learning algorithm's task is to output a prediction algorithm. So it has to output another algorithm. And this prediction algorithm really, so there's a learning algorithm that sees the training data as input, and then it chooses, based on this training data, some prediction algorithm to output, perhaps among a predefined set of possible output prediction algorithms. It'll be a little bit more formal on the next slide. So it produces this prediction algorithm, and then this prediction algorithm can be used to make new predictions on data afterwards, right? So if we feed it one of these images, it might be able to correctly predict the label of whether this is a mammal or not. Right? So, okay, so that's the basic setup. And in addition to this, so what's the goal now? The goal is that this prediction algorithm should be good not on the training data that we have available, but on some data distribution that's generating new images for us, right? So this data distribution has generated the training data, but also we want to make predictions on a new image from the same distribution. That's the basic idea. So produce correct predictions under this data distribution that gave us our training data set. Okay, so if we have to be a little bit more formal in binary classification, right, I guess we typically think of it as there's an input space X, input domain X. This is where the images come from. And there's an output space, in this case, just binary classification. There are just 2 possible labels, 0 and 1. And the learning algorithm then is a mapping from a n training point, so that consists of an input element, the input domain, and a label. And it should produce a predictor, which is just a function or a mapping from the input domain to 0 and 1 again, right? So this is some predictor. Okay, then the next ingredient is this unknown data distribution over the input domain. So the learning algorithm doesn't know what the data distribution is. And then we have this realizable case. So what does this mean? So this means that there is some predefined function class that we call H. It has a particular VC dimension D, and I'll just summarize what that is if you haven't seen it. And what we assume is that there's some unknown function, a target function H star, that belongs to this hypothesis set. And this H star is what assigns the labels. So the training data set consists of these pairs, xi, which is an element of the input domain, and H star of xi, the correct label of this training data point. And the assumption is that this training data set was obtained by drawing each of the xi's IID from this distribution P. Okay. So this is generated the training data set, and then we're looking for the most part of this talk on the PAC learning setup, dating back to the 80s. And here, what we care about is really the so-called error of this hypothesis, so the function that we output, the prediction algorithm we output. And it is just defined as the probability over a fresh data point from the distribution P, that whatever predictor that you output, this is this H hat of S on the training data set S, the probability that it misclassifies a new data point from the same distribution that the training data was obtained from is as small as possible. This is the goal. So the goal is really to produce a hypothesis that minimizes the error under the same distribution. Okay. So just for those that haven't seen the VC dimension first, let's just quickly recap what it is. So the VC dimension is just a complexity measure of this hypothesis, right? So how complicated can these hypotheses be? It's defined as the D, so that there's a set of D samples that can be shattered. I'll find what that is in a second. And no set of D+1 points can be shattered by this hypothesis set. And shattering is just, if I want to shatter D samples, I have to be able to generate all the 2 to the D possible labelings, right? So it's binary classification of 2 to the D labelings. So they can all be realized by some H in the hypothesis set, then we say that shadows is key points. So we have an example, for instance, if your input domain is R1, this points in the real line, and your hypothesis set is the set of all hyperplanes. And now one hyperplane is just a threshold, and everything on one side you say 0, and everything on the other side you say 1, and you can flip which side you say 1. So if we want to check whether we can shadow 2 points, here's an example of 2 points. We have to check, can we generate all 4 possible labelings using a hyperplane? And indeed we can in this example. It's not too hard to see that there's a hyperplane that generates all of them. Okay. So, and in general, okay, I guess we don't check, can we shadow 3 points? I think you could quickly convince yourself, no matter what 3 points they choose on the line, there's no hyperplane that generates this labeling with the 2 outer points classified as say red or 0, and the innermost one classified as 1. So the VC dimension here is 2, and generally you can show that the VC dimension hyperplanes .d is d plus 1. So the VC dimension is just I guess a complexity measure of a hypothesis set that turns out to be the correct measure to look at when we want to know how hard is the learning task. And this realizability assumption we mentioned before is just saying, if your hypothesis set, for instance, instead of all hyperplanes in RD, we're assuming that there is a hyperplane that correctly labels all data under the data distribution. This is this realizability assumption that we look at in the beginning here. So what is I guess the most natural learning algorithm in this realizable setup? It's probably empirical risk minimization. So what is this algorithm doing? It's basically saying, if I get a training data set, I will look for a hypothesis in my hypothesis set H that correctly classifies all of the training data, right? So all the predictions on the training data is equal to the true label. And because we assume that the label function H star is in the hypothesis set H, we can always find such a function, right? There might just be multiple choices for which one to use. So we can always find one, and we can just say output an arbitrary one. So the learning algorithm here really, this is very small, but when it gets a training data set, what it does is it just outputs a prediction algorithm that correctly labels all the training data. So how well does this perform? And this has been understood for a very long time, that if I just output an arbitrary hypothesis that correctly labels my training data, then with probability at least 1 minus delta over the training data set, so with high probability, the error of this hypothesis I produce is order d over n log n over d. So n is the number of training data points I had available, right? Plus a log 1 over delta over n. So dependency on the data probability. And this is actually tight, right? So this has also been known for a while. This is one example. There are several low bounds establishing tightness of this for, if you run empirical risk minimization, this is really the best you can hope for. In fact, any algorithm that outputs a hypothesis from the hypothesis set cannot do better than this. So then this is the optimal guarantee that you can have. In particular, this d over n log n over d is the interesting thing. But even though we're in this realizable case, we promise that the true labeling function belongs to the hypothesis at H. Maybe you could do something different, right? Maybe your prediction algorithm is not just some hypothesis from the hypothesis set, but maybe you're doing something strangely combining multiple hypotheses in some non-trivial way. And if you look at that case, then the only lower bounds that were available is saying d over n, so this without this log n over d. Right? So there's this gap between the upper and lower bounds. And this gap was actually around for a very long time until work by Steve Hanneke in 2016. So he gave the first algorithm that has this optimal error of d over n plus log 1 over delta over n. So it's a really nice result. And I'll try to show you what does the algorithm do. I won't go into the analysis, I'll just sketch what it looks like in this example here. Okay, so his algorithm is based on this procedure for generating subsamples of the training data set. So you have this subsample procedure, it takes 2 arguments, S and T. Think of it as S is a training data set to begin with, and in the beginning, T is the empty set. So if this is your training data set, these squares are just training data points. What you do is so we have a base case. If you have less than 3 data points, you just output as a subsample S and T combined. So let's ignore that case for now. So otherwise, you take your training data set and you split it into 4 pieces. Okay, and they all have equal size. So they all, you don't have rounding, maybe a 0 is a little bit smaller, but generally just partitioned into 4 equal sized pieces like this. And then you do some recursion here. So you have 3 different recursive calls to this subsampling procedure. So So what you do is just for every choice of either S1, S2, or S3 that you can leave out, you do a recursive call where your new training data set is the first chunk is 0, and the new set T is whatever it was before, and then you add to it 2 of the 3 chunks, S1, S2, and S3. So it's going to look like you have one recursive call that looks like this, right? This is your new S, this is your new T, the pink part here, and the gray part has been left out. You have another recursive call where you leave out the second part, and you have a third recursive call where you leave out the third part of this training data. Of course, now you recurse on each of these because we call this a subsampling procedure. Again, you're still not in the base case, right? You have 4 training data points left, so you're going to partition it again into 4 pieces, and then you're going to do these 3 recursive calls where you leave out either S1, S2, and S3. It's going to give you these different subsamples here. T is now these pink sets again. And I guess now you're at the base case, the training data set S is size 1 here. So you just output the full, both the green and the pink data points here as a subset of the full training data set. Okay, so you generate all of these many subsets of the training data set. We leave out the gray parts. And when this recursion bottoms out and finishes, you have all of these different subsamples. So now what does this algorithm do when you've created all of these many subsamples of your training data set? What you do is you find a learning algorithm, you take all of these subsamples here, and then you run empirical risk minimization on each of these subsamples, right? So you just run this algorithm, this naive algorithm, you look at the hypothesis of the training data, you find some hypothesis in H that correctly labels all of the pink data points. And crucially, you're not looking at the gray data points when you're doing it, right? So your algorithm is kind of independent of what's happening in the gray parts of the training data when you're running it on S1, for instance. So you're just looking at the subsample and doing empirical risk minimization. And finally, you do a majority vote among all of their predictions to give your final prediction. This is his algorithm. And what he showed was that you get this optimal error by doing this kind of non-trivial recursive partitioning of the data. The analysis is very non-trivial, and I think for this talk, I won't have time to go into how it goes. There's some inductive argument showing that the error gets better and better as you go up these recursive layers, and leaving out these pieces of data somehow helps you, but we won't get into it here. I guess you have 3 recursive calls on a quarter of the data set size, so the number of these subsamples is log n to the log base 4(3). So you get this about n to the 0.79 many of these subsamples. So you're doing quite a lot of, you're training quite a lot of these here as by.
How do you split into S0?
Say?
How do you split into S0?
You just, so you see the data is basically, I guess it's IIT sandwich, you just partition the first quarter, the next quarter, the next quarter, and the last quarter. Yeah, so nothing special there. Yeah. Okay. So, okay, so now I guess we're getting to the first paper that I wanted to talk about in this work from COLT’24, called Bagging is an Optimal PAC Learning. So the starting point of this work is Hanneke's algorithm here. I think it's a beautiful theoretical result. You finally got this optimal sample complexity for PAC learning after like 30 years or more after these original results. I think if you look at it from a written point of view, maybe it's not the nicest algorithm. You have to do all of this subsampling to get this optimal algorithm. There are quite a lot of these subsamples, like n to the 0.79 of them. They're linear in size in the full training data set size. So you're going to get a slow learning algorithm, right? You have to, whatever algorithm you're running, you blow up the runtime by a factor n to the 0.79. Also, when you need to make new predictions, you also have to ask all of these hypotheses you trained, what should the label be, and do a majority vote among all of them. So that also slows it down. But you can also ask, okay, is this used in practice? And no, it's not really used in practice, right? No one's implementing this. Because one reason is it's kind of slow, but maybe another reason is that there are also practical heuristics that perform just as well or better than this. And so what we're really looking at in this work is really, is there a simpler algorithm that is also optimal for this practical setup? Maybe even a practical algorithm that people are using in practice or could use in practice. And so, so one algorithm that we want to look at that looks a little bit like Steve Hanneke's algorithm, but somehow simpler, it's due to Breiman from 1996. It's called bagging or bootstrap aggregation. It's kind of the simple version of random forest. So it's used a lot in practice. I think I think the original paper has 30,000 citations, so it's, it's not a theory paper. Otherwise, this would not happen. I think maybe, except for a few of them. But what is this bagging doing? So bagging is I guess a heuristic where when you have a training data set S, you sample from it with replacements. So you're going to a number of times. So the original bagging procedure doesn't say how many times, you just do some number of these subsamples until you're satisfied. So my twist to it, okay, we're going to do it a logarithmic number of times. So we're going to do a logarithmic number of subsamples in SI. Each of them, we're going to sample, say, half of the training data with replacement. Any constant factor will work for the analysis. So we're just we take our training data set and we just sample with replacement, say a constant fraction of the data points. So you can get copies of the same data point. If you, and then you're going to do this a logarithmic number of times. Create all these subsamples. And then what bagging does, also the original heuristic, is just if you're in binary classification, you just train a classifier on each of the subsamples and you do a majority vote. And this is your prediction. Whatever it outputs, that's your prediction. So the result of this work here from 23 is that if you do this bagging procedure with just log n over delta many of these subsamples, then you also get an optimal PAC learning outcome. So you get this optimal d over n plus log 1 over delta over n sample complexity for PAC learning, which matches Steve Hanneke's algorithm. The analysis here is unfortunately even worse than Steve's. It's using his analysis kind of in the middle of it. So it's quite lengthy and heavy to go through. So that would be the only thing I could focus on if I wanted to try and explain it. But if we compare the two, I guess the nice thing is that now you only need to train a logarithmic number of these ERMs, and you only have to go make a logarithmic number of predictions in your final majority vote to make your predictions. So that's great. This is used in practice. I think is a nice upside to it. I think maybe one fun fact is that this algorithm was around for 20 years before Steve Hanneke's algorithm. So kind of the answer was out there. The algorithm that got the optimal sample complexity was already known. I guess also that it's being taught in most undergrad machine learning. I was teaching it before this result for a couple of years, just without any guarantees, which was maybe not so satisfactory. Sent this heuristic, but that's what a lot of this ML practice is. Okay. So let me now move on to another paper from last summer's COLT, joined with Ishak Adnali from UC Berkeley, and my own student, Michael Müller-Hüskor, who made some parts of the slides, and Nikita Tsiwatowski was also at Berkeley Stats. So here the title is Majority of Three, the Simplest Optimal Learner. So here we're going to look at a slightly different setup than we just did before, almost the same. So the result we just talked about was in this PAC learning setup where you want to, with probability 1 minus delta, you want to make the error small. Right? So you have this high probability guarantee. In this work here, we're going to look at a slightly simpler model called the prediction model from 1994. And here, the only thing we really want to is to produce a hypothesis whose expected error is small. Right? So we're kind of sacrificing this with high probability guarantee. So what can we do in this setup? So here there was actually an optimal algorithm known for a long time, since this original paper in 1994. It's called the one inclusion graph algorithm. So I'll try to explain what it does here. So it also does for Hausler, Littlestone, and Wormuth. So what you do here, if I have a training data set, it looks like this. So I have 4 data points with 4 different labels. And now I want to make a prediction on a new data point X. So what I do now is I build a so-called projection graph of the hypothesis set onto my training data points and X. So what does that mean? It means that I look at my hypothesis set and then I look at all the possible ways that it can label these 5 data points, the training data and X. So all these nodes are the things that can be realized by a hypothesis in H. Then I connect every pair of nodes that disagree in exactly one prediction. So for an edge between any pair of nodes with, I guess, Hamming distance of 1. And now the interesting kind of thing that I do now is I look at this graph. I ignore which one of them is my data point to make a prediction on. I just look at it as I don't pay attention to who is X. So now I orient this graph to minimize the maximum out degree. So somehow I pick an orientation of all the edges so that the maximum out degree is as small as possible. And finally, when I now need to make my prediction on X, what I do is I look for the nodes in this graph that are consistent with these 4 labels that I know of. Okay. So there are at most 2 such nodes that are consistent, right? Because, well, I guess there's only the point X that you could have different predictions on. And so in this case, right, maybe these 2 are the nodes that I have to choose one of them. Which one do I believe is the true labeling function? Like we know the true labeling function is in the hypothesis. So one of these 2 is the true one, and now I have to make a choice what to predict for X. Right, I have to go with one of those 2. And the algorithm is just to say make the prediction in the edge direction. Okay, so basically this edge points to this node down here. So I will predict 0 in this case here. Okay. And now I guess you can. I'm not going to give the analysis, but the main idea is that you're basically going to make a mistake if your true label is here, but you predict down there, which means you kind of have an out edge. So kind of the out edge is corresponding to when you make a mistake. There's something about ignoring who's your training data and who's X, so there's some symmetry that you can play around with. Anyways, they showed that the error of this algorithm becomes D over N. So the expected error of this algorithm. So it's not a trivial thing to prove. And the key idea, basically the error is going to be the max out degree over N. That's the expected error. That's what they prove. And then there's a lot of work to show that if my hypothesis has BC dimension D, there's always an orientation with max out degree D. So that's kind of the main ingredients in this work. Okay, so now we have, I guess, 3 different algorithms in this prediction setup, because I guess the other ones with high probability guarantees, they also give you the optimal expected error. If you want to look at this one inclusion graph algorithm in the high probability regime, you could maybe conjecture that it's optimal, but the only thing that was known was basically Markov's inequality on top of it. Then you get some bound like D over delta N. And this was actually shown in 23 by, I guess, the 2 co-authors on this work and also 2 other students at Berkeley, that this is actually tight. So you can come up with examples where you will pay D over delta N for this one inclusion graph algorithm. So it's not optimal in the high probability machine. Okay. So now we have 3 different algorithms. I guess, so what can you say about them if I want to now be pessimistic? You can say the first one here is again slow. You have to build this graph. It can actually be quite large. You can have basically N choose D, many different ways you can label these endpoints. So it can be kind of large, and it's not clear how to do it efficiently. In Hanneke's algorithm, you have to do the subsampling, all these many subsets that you had before. And now I guess I want to say that the bagging one is not so great, even though before I praised it. So you still have to do a logarithmic number of these ERMs, right? There's still some work to do. You get this logarithmic overhead in your runtime. Okay, so can we do even better and something even simpler maybe? That's kind of the starting point of our work. So what is the simplest optimal algorithm in this prediction model is what we ask, right? What's the simplest thing you can think of? Maybe let me also mention that ERM in itself is known to not be optimal, right? There was this D log N over D over N bound I mentioned in the beginning. There is this logarithmic factor also on the expected error of ERM. So just training one classifier is not enough. So we're just looking for the best. We want the optimal expected error. And here our algorithm, this is majority of 3. I think this is, so majority of 2 is undefined if they disagree. So majority of 3 is kind of the simplest thing you can think of. Take your training data set, partition into 3 disjoint equal sized pieces, run empirical risk minimization on each of them and do a majority vote. So, yeah.
Yeah, sorry, just step back for a second. Is there like, I feel like I don't have a consensus intuition for why ERM like would not be optimal, right? It seems like if this is like give us an amount of data, like the best you would hope to do is like match it.
Yeah. Yeah, then I guess okay. So you can maybe show you I can show you the lower bound example afterwards. Maybe there's a lower bound proof that you can kind of fool anything that does ERM. It's not a trivial proof, but you can cook up some data distributions where basically ERM. Since you have to choose something in the hypothesis set, you can fool it into making a lot of mistakes in data that you didn't see. That's kind of the, whereas if you do majority vote, you cannot, this trick to fool it, as soon as you train 3 in this example, 2 of them are going to be correct on this left out data.
Is the point there then with these like alternative ones that you're seeing more data
I think the main issue is actually you're leaving out. Okay, so when you train this one, you're leaving out this part of the data. So if this one makes a lot of mistakes, you're going to see some of the mistakes in here because they're independent of the data that it was trained on. But then the other two are trained on the mistakes that this one is making. So they kind of correct each other's mistakes in some sense. That's kind of maybe one intuition for why it helps. Like, so if you have two that are correct whenever one is wrong, and you do a majority, that's going to help you. Maybe some intuition to that why. Okay, so this is the learning algorithm, and our main result in this work is that this gets the optimal DOA expected error. And this proof is also very simple. I think I basically give you the whole proof here. And it's much simpler than the previous proofs of optimality. So let's try and see how it goes. So there's a kind of like, okay, so what's the first observation we need? This is a trivial one. For the majority to be wrong, at least two of them has to be wrong. Right? Okay, so that makes sense. So if this is the input domain X and this is H star, then I guess they all make their predictions, and for them to be wrong, at least two have to be wrong. Okay. So now, I guess the second observation is that if I look at the distribution of this classifier that I'm outputting, if I run the same ERM algorithm, maybe there are different algorithms for doing running ERM, but if I run the same one on all three pieces of the data, then because the training data is IID, so is the distribution of this classifier, right? So they also have the same distribution. So now I can say, okay, what is the expected error of this when I get a training data set of size n? Well, it is, so what are we saying here? So just writing this expectation over a fresh data point indicator for whether you're wrong. And then we're saying, okay, so we're using this fact, two of them have to be wrong. So I can do a union bound over all the choices of two of them that can be wrong. The three choices for which two are wrong. So that gives us a factor 3 times just I guess the expectation over two data sets of size n third of, I guess this is the probability that they're both wrong. And so, okay. And this is again by this IID assumption that you can just focus on S1 and S2. Okay. Then we just flip the order of expectation now. So we're going to move the expectation over X out and the expectation over S1 is 2 in. And then again, we're using that these are independent. So I guess I can write this indicator that they're both wrong as a product of two indicators. The first is wrong, the second is wrong. By independence, it's the expectation of this product splits into the product of the expectations. And again, by IID, these two expectations are the same. Right? So the probability that your error is the same. Both of them. Right? The expectation over S1, but the probability over S1 that you're wrong on X, and the probability over S2 that you're wrong on X is the same probability. So you just get this, it's the probability over S1 that you're wrong squared. Okay. So, okay, so now we have to work with this. And so what we do is that let's try to look at some X in the input domain. So let's zoom in on this one. And then we're going to define p sub X as just this error, right? The probability over a new data set of size n third that the predictor you produce is wrong on this X. This is Px, the probability that you're wrong on this X when I train a new predictor. So then, I guess all three of them, because they have the same distribution, right? They are all wrong on X with probability Px for this training data. So then this is just Px squared, right? This probability that you're wrong. Okay. So now our next key idea is to say, okay, now let's try to look at the input domain and partition them into how often is this ERM algorithm wrong on this particular data point X. Defining these regions consisting of all in the input domain where your ERM is wrong with the probability that lies in the interval from 2 to the minus I to 2 to the minus I plus 1. So you can kind of think of it as some R1, that's where your ERM is almost always wrong on these data points, like constant probability, and then get these regions where it's rarer and rarer that you're wrong. So now we can say, okay, what is this probability or this expectation? Well, it's the sum over all these regions, the probability of getting a data point in this region and the expectation condition on getting a data point in this region. And now, because of the definition of these regions, this the expectation of px squared, given that we get a data point from region I, is just at most 2 to the minus I plus 1, and then you square it. Like that's how they were defined in terms of how often you err in these regions. So now we have this 2 to the minus 2i plus 2 times the sum of the probabilities that I see a data point from each of these regions. Okay. So all that remains now is really to bound this probability of seeing a data point where you often make a mistake. So now we want to show that these regions are small. Particularly if you err a lot in the region is small. That's the main idea. So here again, so how many data points do we expect to see from this region Ri? We're going to expect to see the size of the data set is 1 times the probability of seeing a data point. And just linear expectation. So we're going to see this probability times n over 3 samples from it there. Okay. Now, one important point is that since we're in this realizable case, the hypothesis we train is going to be correct on all of its training data, right? In particular, it's going to be correct on those NI points that it sees from this region and everything else as well. And so if we use these original analyses for ERM, if you look carefully at what it's doing, it's proving a so-called uniform convergence bound. So it's basically saying everything that's correct on all the training data has a small error under this distribution. That's what they're showing. Which also means that this ERM that I'm training here, it's correct on all of this and some more. And that's enough to conclude that under this distribution, conditional distribution of a point from Ri, its error is small. It is as if it had NI data points from this distribution. It doesn't matter that it sees more data. That doesn't harm it because it will perfectly classify all of it. So you can really, so this algorithm's expected error or data point that is drawn from conditioned on coming from this region Ri is basically this ERM bound d over ni log ni over d. But at the same time, we also define this region Ri to be so that we often make a mistake, right? We also have a lower bound on how often we misclassify these data points, right? So we also say that your expected error on a point from this region is also at least 2 to the minus I. And now we just combine these two to get a bound here. I think this is just combining them, expanding what ni is. It's I guess this probability x is in Ri, n over 3. And if you work with this inequality, not too tricky to see, but basically what you end up with is that the probability of seeing a data point from this region is order 2 to the I times d over n. So it's just playing around with it. This is what you get. So now we have, so basically what it's saying is if you often error on this region, the region has to be small because otherwise the total error would be too high. It's kind of the intuition. So now we can combine this in here. We have this bound that the probability of seeing a point from this region is 2 to the I d over n. If we insert it, now we have this 2 to the minus 2i times 2 to the I times an I. So that goes down geometrically faster. So it's dominated by the first term, and you just get this order d over n. And the real trick here was that this part, the 2 to the minus 2i, that was this px squared. That's because you have the two of them have to error, and they're independent. So you get this px times px, so you get the 2 to the minus 2i that kills the 2 to the I times I. So that's the whole part of the analysis. This makes it go away. That's really the full analysis of this algorithm. So if you just partition into 3 pieces, you do a majority, train the ERM on each and do a majority vote and get this optimal error. I guess you could ask yourself, is this also optimal in the high probability regime? We had a question mark in our time. We actually, I guess I would conjecture that it is optimal for PAC learning as well. We couldn't prove it, but we proved something very close. We proved that its error in the high probability regime is d over n times log of the minimum of n over d and 1 over delta. And then an optimal, the second term is optimal. So I don't know, is there this log 1 over delta dependency or not? I don't think there is, but we didn't manage to prove that it's not there. Okay. So can we get rid of this log term? I think this is interesting. Okay, let's I guess take the last result from FOCS’24, which is together with Steve Hanneke and Nikita. So this I guess called revisiting agnostic PAC learning. So this one here, I'm just going to give you the main high-level ideas. It's more technical than the other one, so I don't think I'm going to get into many details, but just try and show you the main idea of the algorithm. So before we look at this realizable case in all the previous ones, right, so we assume that H star belongs to H, and we want to get something with error going to 0 as quickly as possible. Here, we are not assuming that the unknown target function lies in H. Instead, we want to be competitive with the best one in this class H. So here we have some, let's call it tau. This is the best error you can get by using some hypothesis in H. And the goal is just to produce a hypothesis whose error is close to this. So that's what we're trying to do. Okay, so here again, empirical risk minimization makes sense. You just find a hypothesis minimizing the number of mistakes that you make on your training data. And this is also well understood. The bounds a little bit more complicated, and this is even ignoring some lower order terms. If tau gets very, very small, it gets more complicated, but for most values of tau, this is the bound. So you get this, your error, if you do empirical risk minimization, is this tau plus, you have the square root term, this is tau d log 1 over tau over n is the interesting fact here. The other part is optimal. And the only lower bound here is without this log 1 over tau factor that you see here. So that one's gone in the lower bound. So it's again this logarithmic gap between ERM and what you can prove for lower bounds. And this is the only lower bound both for proper and improper algorithms. Okay. So I mean, these are just the same bounds that are stated again. So what is our results? We have two results in this work. One of them is showing any proper learning algorithm. So again, if you insist on outputting something from the hypothesis that you're not doing a majority vote or something, then you have to pay this log 1 over tau. It is there. So you cannot do ERM is the best strategy you can do. I think the more interesting thing is a new learning algorithm that is improper, that has an optimal error here of this square root tau times d plus log 1 over L over n. Again, this algorithm is not optimal if tau is very small, and I'll show on the last slide what's the suboptimality factor. But for most values of tau, it's optimal. So I think I'll just sketch what are the main kind of ingredients that go into them. A lot of things that go in there, but the main thing to look at, what drives the whole argument is we're looking at hypotheses that are close to optimal. So we're going to define H star to be all the hypotheses whose error is basically of the magnitude you would get if you ran ERM. So these are the ones that are pretty good, but not optimal necessarily. So we're going to look at this H star, all the ones that are pretty good. Then you first make one key observation. I won't prove it here, but it's kind of interesting. We have one observation is that if every pair of hypotheses in this set H star, so all pairs of hypotheses that are near optimal, if they almost always agree on their predictions. So, and what do we mean by almost always? That the probability that I get a data point where they disagree from this distribution D is at most tau over log 1 over tau. If this is the case, then we can show that ERM actually works better than all the previous guarantees. You actually get an optimal bound if you run empirical risk minimization. If you have this promise that any pair of hypotheses that are near optimal are basically almost the same hypothesis. That's kind of what it says. And the intuition is really if you just have one of them that performs well, then because they look so much alike, they basically all perform well. That's the main intuition in this. So that's kind of first, okay, so if they all basically make the same predictions, then you can just run ERM. And then we say, okay, but what if this is not the case, right? So we want to, what happens if there are hypotheses, just one pair that disagree a lot in their predictions, right? So they disagree with probability tau over log 1 over tau at least if I draw a new data point. So then we look at again like one of these regions of the input domain. We're gonna let's look at the region where they disagree. So let's call this R. So then we inside R, one of them is wrong and one of them is correct, right? Because they have different predictions. There are only two labels. So one of them is correct and one of them is wrong. And outside R, either both of them make a mistake or they're both correct because they make the same predictions. So what does this allow us to do? It said, okay, let's look now at the sum of the error of both of them. On one hand, we know that they're both near optimal, right? So we add them up, we get 2 tau plus this suboptimality factor. On the other hand, we just said, well, what is the chance they make a mistake? So one of them is wrong if you get a data point from this region R, exactly one of them is wrong all the time. And then they're both wrong if I get a data point that's not in R, and the first one is wrong. Like if one of them is wrong, both of them are wrong. This is kind of, okay, so we write it like this. And then we can rearrange this inequality. We know this term is large. This is like, we assume that they disagree a lot. So this is omega tau or log 1 over tau. Move it to the other side. It's divided by this 2 times the probability that you get a data point where they agree. If you play around with it, you can conclude for the, except when tau is very small, again, I'm just gonna ignore it. But the basic point is that you get to subtract, when you get a data point where they agree, the probability that you're wrong is not so large. It's basically this tau plus this suboptimality term that you got from theorem minus this tau over log 1 over. So you somehow subtract something from the error probability here. And maybe one crucial point is that if tau is not too small again, so again some assumptions on how small can it be, this term is larger than, basically if it's significantly, if tau is just bigger than d over n, sufficiently bigger than d over n, this term is going to dominate among those two. So you're subtracting something off, right? So you basically, what this gives us is that as long as I get a data point where they agree, somehow everything became easier. Now the best hypothesis that I can find is better than tau in performance. Like before tau was the best possible, now you can do a little bit better when you have data points where they agree. And also the size of this disagreement region is not too big. So basically now if we combine all of these observations, we had, okay, if they all the near optimal ones rarely disagree, then you can run ERM. If there is a pair that disagree a lot, then whenever they agree, the data distribution is a little bit easier. You can kind of, there's something that does better than tau. If you do tau minus tau over log 1 over tau, so you can do something slightly better. Also the region where they disagree is small, it's not too big. And so the last kind of ingredient is to apply this recursively to kind of drive down the best performance. This is tau, we want to reduce it quite a lot. So what we do, the final algorithm, I won't do into analysis, but basically we repeat log 1 over tau, log 1 over tau many times. We're going to, basically in every round, we're going to find a pair of hypotheses that disagree a lot and are near optimal. Okay, so basically first you're going to say, okay, let me extract the training data set where all the previous pairs agree. This is kind of like the region that got a little bit easier every time. And then you're going to look for a new pair of hypotheses that are both near optimal on this data set, and they disagree a lot. If no such pair exists, we're done. And if you can find such a pair, you just keep going. And then finally, once you're done with this, you take the rest of your training data and you do 2 pieces. One of them is all the data where all the pairs so far agree. So this is kind of the region that got easier and easier and easier. And then you have the remaining data that's this is not equals. You run ERM on both of them to get 2 hypotheses. And then the final algorithm is a little complicated. So you're going to ask all these pairs if there's a pair that disagree on this prediction. If there is, we're going to use the one that's trained on all the data where there's a pair that disagree. And otherwise, we're going to use the classifier that was trained on where everything agrees. So kind of the intuition is really every time we train such a pair, we're kind of removing a little bit of the difficult part of the input domain. So basically, whenever they disagree, this is kind of the difficult part, we remove it and we train a bunch of those. And then everything that is left, we have reduced this tau enough that we can run empirical risk minimization on it afterwards and get the optimal boundary. That's kind of the main idea. So you just run empirical risk minimization there. Because when all pairs agree, the distribution has become very easy. Drove the tau sufficiently down. And then the other part is we show, since this region is very, very small, you can actually do empirical risk minimization there as well, and it still works out optimally, but it's a longer argument for that. But that's the main idea. Because you keep it small, you can afford to do empirical risk minimization. Right. So that's kind of the main result in this one is new optimal improper algorithm. This is the full analysis of it. So it has this basically looks like the realizable case. At some point has to become the realizable case if tau is small enough, right? And we have some polylog factors sitting there. So it's optimal as long as tau is not too close to D over N types of polylogs. So yes, some interesting questions. Can we get optimal full range of tau? Is there similar optimal algorithm, like a majority of 3 type of stuff with a simple analysis? This gets lengthy. Bagging majority of 3. We had this hard instant that proved the lower bound for this problem. Any kind of hard instant we come up with, running majority of 3 or bagging or something would work. So, but we couldn't figure out how to prove it without this realizability assumption. Maybe this is something practical to be derived from this algorithm here. It's not clear. Also, it's not clear how can you even quickly compute 2 near optimal hypotheses that disagree a lot in their predictions. Right? That's not obvious that this is even tractable. Yeah, so it doesn't give anything in practice. Yeah, so I think that was kind of the highlight of these 3 results. Thank you.
You're relying on this assumption of 3 dimension D.
Yeah.
Which is a very strong assumption. Because it's still a very adversarial distribution. So yes. Another one is if you have a distribution that satisfies some assumption, that other assumption of the distribution could allow you to prove similar results, even if you don't have this dimension assumption on the hypothesis class.
Yeah. I guess our work. It's a natural question. I don't think any, like all of our parts of our analysis is very tied to species dimension.
In general, people try to find combinatorial classification of when we do learning under distribution classes, families.
Yeah.
This seems to be not tractable because
yeah.
But you can ask a simple question, which is, can you make assumptions under which some of these algorithms become, you know, that still work?
Yeah.
Even though your hypothesis class is not very well about those distributions, right?
Yes. That's true. Yeah, I think what we're really using in the first one is really this fact that if you're training on superset, like if you add more data to it, and you have this small set that comes from a particular region, and you add more data to it. If you train on all the data, your performance still is great on the small data set as it is, and if you only had that piece of the data. Maybe there's some other assumption that you could capture this kind of property. I don't know. Yeah, maybe something like that. Yeah.
Here's a question. Yeah. Oh.
So the question, oh, you cannot see it there. So the question is, does optimal improper learner use bagging by optimal proper learner in the realizable case? Avoiding more X in the data space. I'm not sure. Again, this is the first part of it. I guess if you could prove that bagging was had this guarantee without the log to the fifth n over d, like for any value of tau, I guess by plugging in tau is 0 is you get the realizable case, and then I guess you would also get an optimal algorithm in that case. So I think so. I don't know about this enumerating overall X in the data space. I don't think bagging is not, maybe I misunderstand the question, but for bagging, you're not enumerating overall X in the input space. It's only for the analysis and majority of 3 and so on that you're even looking at the whole input space. Yeah. I hope that answers it.
So sorry. The question is about the proper learning. Right? Are you able to do proper learning in the realizable case? By taking the voting hypothesis from either bagging or the best of 3.
Still not sure exactly again. So you're saying in the realizable case, if you want to do
proper learning by outputting a hypothesis from the hypothesis class rather than improper learning.
Also, so you're saying, okay, if you can get it, yeah. But so that lower bound showing that any proper learning algorithm will have this log n over d factor. So in that sense, I don't think you can look at the output and like look at all the hypotheses that make up bagging a majority of 3 and choose one of them. I don't think that will not work. Yeah, that still gives something proper, and the law bound is saying any proper learning algorithm, not just TRM.
I see. So even the inefficient distillation process doesn't work. So what
Exactly.
I see.
Yeah, exactly.
Any other questions? Okay, so Kasper is visiting till Wednesday, so if you want to meet with him, he will be here. You have an office here, right,
I
Kasper?
don't know if it's, yeah, it's over there.
Yes, so he's here, you can meet with him. So, thank you for the great talk.